All right, in this video, we're going to talk about section 5.5, dealing with the substitution rule when we're dealing with the integrals. And out of that section, we're going to be evaluating indefinite integrals using substitution when the substitution is given. Also, we'll evaluate indefinite integrals using substitution when the substitution is not given. Then we'll evaluate integrals using substitution when additional steps are also needed, and evaluate definite integrals using substitution. Okay, now, when we use substitution to integrate expressions, we're going to be doing the reverse of the chain rule. And let me give you an illustration of just that. Let's say I had this function, y is equal to 4x squared minus 5, and that quantity is cubed. All right, so if I took the derivative using the chain rule, that's of course dy dx, which I'll label as that. Now, when we use the chain rule, we're going to bring the exponent in front, or bring down the power, that's going to be the 3, multiplied by, and then we copy what's in the parentheses over that 4x squared minus 5, and that would be to the 1 less power. 3 minus 1, that's 2. And then, of course, we have to multiply this by the derivative of our inside function, which is in this case 4x squared minus 5. Its derivative will be 8x. Okay. Now, let's say if I wanted to write this as a differential, then I'll just write this as dy is equal to 3 times the quantity 4x squared minus 5, and that's squared, times 8x dx. That would be our differential here. Now, we're going to work backwards here in this case here. So, to find out what y is, and I'm going to show you how this is done when we work backwards. We're going to take the integral of this right here. The integral of 3 times the quantity 4x squared minus 5 quantity squared times 8x dx. And this is where we're going to be using what they call a u substitution. So what we're going to do here is let u equal to, and I'm going to pick the one that's more complicated, like the 4x squared minus 5. And then I can find out the derivative of u, which will be, of course, bring down the 2 multiplied by the 4, you get 8. Copy the x over to the 1 less power. So it'll be 8x dx. And of course, the derivative of minus 5 is going to be 0. And then we use an appropriate substitution. We can do the substitution here. So in this case, this 4x squared minus 5, that's going to be our u. And then I got 8x dx, that's this part right here. That's going to be du. And since that 3 is a constant, I can pull the constant out in front of the integral symbol. So it'll be 3 times the integral of, now the 4x squared minus 5, that's going to be u, so it'll be u squared. And then the 8x dx will just be du. And then I'm going to integrate by using the power rule. So I'll bring down the 3. For the u squared, the integral of u squared du, I'm just going to increase the power by 1. So it'll be u to the 3rd divided by the new exponent of 3. And since I have an indefinite interval, I'm going to have plus c. Now, if I simplify this a bit, these 3's divide out. And I'll be left with, in this case, y is equal to u to the 3rd plus c. And of course, I have to do back substitution, meaning I let u equal to 4x squared minus 5. So I replace that u with that 4x squared minus 5. So I have y equal 4x squared minus 5. That quantity will be cubed plus c, which is pretty much similar to what I have up here. All right, now that idea is how we're going to use the substitution rule to do our integration of expressions. All right, so here's theorem 5.6. And it says here, if we let u equal some g of x, where g of x is a differentiable function on an interval, and let f be continuous on the corresponding range of g, on that interval, we have this. The integral of f of g of x times g prime of x, and that's going to be equal to the integral of f of u du. Okay. That's just a substitution rule for indefinite integrals. Now, the procedure that we're going to use is this. Number one, you're given an indefinite integral involving a composite function f of g of x. Once you're given that, you're going to identify an inner function u equaling to some g of x such that a constant multiple of u prime of x, equivalently g prime of x, appears in the integrand. All right, so here you want to pick the one where you can find what the derivative of that function would be, and hopefully it would appear in the integrand. Then number two, you're going to substitute u equal g of x and du equaling to u prime times dx in the integral. Then number three, you're going to evaluate the new indefinite integral with respect to u, and then finally write the result in terms of x using u equal g of x. That would be your procedure for using the substitution rule, or what they call change of variables. Now, the disclaimer here in this case is that not all integrals will yield to the substitution rule, and you're going to see that in the few examples that I do in this video. All right, so starting with example 1. Here we got the integral of 2x times the quantity x plus 2, and that's raised to the fourth. And they tell you to use substitution u equal to x squared plus 2 to evaluate the indefinite integral below. So we're going to use that substitution u equals to x squared plus 2. Okay, so here's how we start this off. We start off by letting u equal to that x squared plus 2, which is what's inside the parentheses. And then we take the derivative of u. The derivative of u will be, the derivative of x squared will be 2x. And the derivative of 2 is going to be 0. So du will be equal to 2x dx. Okay. Now, in this case here, I'm going to rewrite this as the integral of x squared plus 2, and that quantity is to the fourth. And I'm going to put the 2x where the dx is. Because you're going to see how this substitution is going to work out. So in this case here, that x squared plus 2, that's your u, and the 2x dx, that's going to be du. So here's what I'm going to have. The integral of this u will be to the fourth power, so it's going to be u to the fourth du. And then after that, we can just go ahead and use the power rule to integrate this, because now it's in a more simpler form. So to integrate using the power rule, I just increase the power by 1. So it'll be 4 plus 1, which is 5. And it'll be divided by the new exponent, which is 5. And I'm going to include the plus c because this is a indefinite integral. With all indefinite integrals, you must include that plus c. Now, I can't leave this answer in terms of u. The final answer has to be in terms of x. So I'm going to do the back substitution since u is equal to x squared plus 2. I'm going to write like this, and I'm going to write this in another way, like 1/5. And then replace that u with the x squared plus 2, and that's going to be to the 5th power plus c. Okay. So that's how we use an appropriate substitution to integrate functions like these. Okay, look at example 2. Here we got the integral of -10 sine of the quantity 5x squared minus 2 dx. And you're told to use the substitution u equaling the 5x squared minus 2 to find the following indefinite integral. Okay. And for the sake of time, I won't do the check by differentiation. If you want to do that, you can always check that it's right on your own. All right, so we're told to use substitution u is equal to 5x squared minus 2. So that's what we'll do here. We'll let u equal to 5x squared minus 2. And then we're going to find out what du is. So all we do there is just take the derivative of 5x squared minus 2. We'll bring that 2 down and multiply it by 5. You're going to get 10. Copy the x over to the 1 less power. It'll be 10 to the first. The derivative of minus 2 will be 0. So we have du is equal to 10x dx. So here we have to write that as a differential. All right, so now let me rewrite this first. Now that negative sign, or the negative sign, I can pull that out in front. So I have a negative in front times the integral of sine of 5x squared minus 2. That's going to be multiplied by 10x dx, which is exactly what I have here for du, 10 dx. And now let's do our substitution here. That 5x squared minus 2, that's going to be u. The 10x dx, that's going to be du. So here's what I'm going to have. Negative of the integral of sine of u du. Negative of the integral of sine of u du. Now let's find out what the integral of sine of u will be. So I'm going to bring down this negative. The integral of sine of u du will have to be negative cosine of u. And then we include the plus c. Okay, that's one of our integrals of our 6 trigonometric functions here. Back in section 4.9, make sure that you look over that set of notes for section 4.9, because the integral of the sine of u du will be negative cosine of u. Now we got a negative of a negative. That's going to be positive. So I can write this as the cosine of, and I'll go ahead and replace the u with what we let it equal to, 5x squared minus 2. So I have cosine 5x squared minus 2. And then plus c. Okay. So that's the integral of negative 10x sine of the quantity 5x squared minus 2 dx. Okay. Now, next we'll look at some more integrals. Now, these are the ones that are not going to be what we call perfect substitutions here, because the first 2 examples were perfect substitutions. Here, there's some that may not be perfect. Okay. So some of these examples show more typical situations that require introducing a constant factor. Like in example 3, let's say we have the integral of x to the 6 times the quantity x to the 7 plus 26 raised to the 8th dx. All right, so here's what we need to do here. I'm going to let u be equal to, now in this case, I'm going to let the u be what's inside the parentheses here, x to the 7th plus 26. Okay. I'll let the more complicated expression be what u is, especially when it's in the parentheses. So my u will be equal to x to the 7th plus 26. And then du, I'll take the derivative of that. Well, the derivative of x to the 7th will be 7. Bring down the 7, copy the x over to the 1 less power. So it'll be 7x to the 6 dx. And of course, the derivative of 26 is 0. Okay? Now, I'm also going to rewrite this as the integral of, and I'm going to put x to the 7th plus 26, and that quantity is to the 8th power, and then put x to the 6th right next to the dx. I'm going to show you something here. I do have x to the 6th dx, but I don't have the 7 up here. However, what I can do here is make this x to the 6th dx. I can get that by itself. It's being multiplied by 7. So the opposite of that would be to divide both sides by 7. So that means I have 1/7 du is equal to x to the 6th dx. Okay. Now I can do my substitution here. That x to the 7th plus 26, that's going to be the u. This x to the 6th dx, that's going to be, in this case, 1/7 times du. So it'd be 1/7 du. Now, and I'll go and do the immediate substitution here. Integral of u to the 8th times 1/7 du. Now the constant is 1/7. I can pull that out in front, so it'll be 1/7 times the integral of u to the 8th du. And from here, I can go ahead and integrate by using the power rule. So I bring down the 1/7, and then increase the power by 1, so it'll be u to the 8 plus 1, which is 9. That'll be divided by that new exponent of 9. And it's an indefinite interval, so I need to include plus c. All right, so now let's multiply 1/7 times 1/9. That's going to give me 1/63. And replace the u, do the back substitution. That u was x to the 7th plus 26. And it's now going to be raised to the 9th power plus c. So that would be the integral of x to the 6 times the quantity x to the 7th plus 26 raised to the 8th power. 1/63 times the quantity x to the 7th plus 26 raised to the 9th plus c. Okay, let's take a look at this example, example 4. And while I'm on it, feel free to pause the video if you need to copy stuff, down off this video. Let's say we have the integral of x to the 5th times the quantity x to the 6 plus 14, and that's raised to the 8th power, dx. Okay, in this case, what I'm going to do here is let u be what's inside the parentheses here. In this case, it's the x to the 6 plus 14. Okay. Now, my suggestion is you might want to just try something if you can. And I know I can't use x to the 5th because that's not going to help me any. So I'll try x to the 6 plus 14 and use that as u. And then du, take its derivative, bring the 6 down, so it'll be 6, copy the x over to the 1 less power. So 6 minus 1 would be 5. So du will be 6x to the 5th times dx. So as you can see, I have almost this right here. I do have the x to the 5th dx. And I'll rewrite this as the integral. Now put the x to the 6 plus 14 raised to the 8th. And then x to the 5th will go with the dx. Well, let me get x to the 5th dx by itself so I can do the substitution. I'm multiplying it by 6, so I'm going to divide both sides by 6. So that means I'll have 1/6 du is equal to x to the 5th dx. So in this case here, that x to the 6 plus 14, that would be u. And then x to the 5th dx, that would be 1/6 times du. And to illustrate that, I have the integral of u to the 8th times 1/6 du. And let me make that 6 look like a 6 that doesn't look all that great. It'll be 1/6 du. Now the 1/6 is a constant, so I can pull the constant out in front of the integral sign. So it'll be 1/6 times the integral of u to the 8th du. So bring down the 1/6. And then to take the integral of u to the 8th, we increase the power by 1 and divide that by that new exponent. So it'll be u to the 8 plus 1, that's 9, divided by 9, and then plus c. Now I got 1/6 times 1/9, that's going to be 1/54, times the u. I'm going to do the back substitution. We let u be x to the 6 plus 14. And that quantity is to the 9th power, plus c. Okay. So that would be the integral of x to the 5th times the quantity x to the 6 plus 14 raised to the 8th power. Okay, now on the next page. Now, there are some cases where the choice for a u substitution is not so obvious, or it requires more than one u substitution for it to work. Like in this example here, let's say we got the integral of x divided by the square root of x minus 9 dx. Okay. Well, what I can do here is let u equal to what's underneath that square root symbol, or underneath the radical, I should say. So I'm going to let u equal x minus 9. Then du will be equal to, well, the derivative of x is 1, so it'll be 1 dx. Or I can just say du will be equal to just dx. And the derivative of minus 9 is 0, by the way. Well, I know I can replace the x minus 9 with the u, and the dx can be replaced with du. But I need something to replace the x with, because that whole entire integral must be in terms of u. I can't have a combination of x's and u's in that integral. Well, let's use that u equals x minus 9. So since u is equal to x minus 9, let's solve this equation for x by adding 9 to both sides. So that means my x here will be equal to u plus 9. U will be equal to x plus 9. So everything will be in terms of u when I do the substitution. Okay? So here I'm going to have the integral of this x will be replaced with the u plus 9 divided by the x minus 9 underneath that radical will be replaced with u, so it'll be the square root of u in the denominator, and dx will be du. So I get the integral of u plus 9 divided by the square root of u du. And I'm going to write the square root of u. Okay. Now I'm going to write the square root of u as u to the 1/2 in exponential form. So this would be u plus 9 in the numerator divided by u to the 1/2. So I have the integral of u plus 9 divided by u to the 1/2 du. And I'm going to break this up by putting each term in the numerator over the u to the 1/2. So I have the integral of u divided by u to the 1/2 plus 9 divided by u to the 1/2 du. And if I divide u by u to the 1/2, that's a 1 minus 1/2, which will be 1/2. Because when I'm dividing powers of the same base, I subtract the exponents. So it'll be u to the positive 1/2 plus. And if I pull that u to the 1/2 out of the denominator, it will be u to the negative 1/2 times du. And I'm going to go ahead and integrate each term here to save a lot of steps and some time. The integral of u to the 1/2 du, we know we increase the power by 1 and then divide by the new exponent. So this will be u to the 1/2 plus 1, that's 3/2, divided by the new exponent of 3/2. Plus, bring the 9 down. For the u to the negative 1/2, we increase the power by 1. So negative 1/2 plus 1 will be 1/2. So it'd be 9u to the 1/2 divided by 1/2. And then plus c. Okay. Now, here the reciprocal of 3/2, that's 2/3. So that'll be 2/3 u to the 3/2 plus 9 times the reciprocal of 1/2 would be 2. So it'll be 9 times 2 times u to the 1/2 plus c. Now let's simplify and do the back substitution. My u was x minus 9, so it'll be 2/3 times the quantity x minus 9 to the 3/2 plus 9 times 2, that's 18, and replace the u with that x minus 9, so it'll be x minus 9 raised to the 1/2 plus c. And I will go no further than this. So that would be the integral of x divided by the square root of x minus 9 dx. Okay. And here's another example of a integral where the u substitution is not so obvious. And sometimes we have to use more than one substitution. Like this one, the integral of p times the quantity p squared raised to the 8th dp. All right, so now let's do this here. I'm going to let u equal to what's inside that parentheses here, p plus 2. So I'm letting u equal to p plus 2. And then I'm going to find out what du is. Du is equal to 1 dp, or just dp. Notice that the expression is in terms of p. Now I know I can replace the p with du, and this p plus 2 can be replaced with the u, but I need something to replace the p with, and it's got to be in terms of u. So, since u is equal to p plus 2, I'm going to solve for p by subtracting 2 on both sides. So that means I'm going to have p is equal to u minus 2. So p is equal to u minus 2. Now, we can do our substitution in this integral. So here we got the integral of this p would be u minus 2 times p plus 2 would let u be p plus 2. So this will be u raised to the 8th. And then dp will be du. Now, if I distribute the u to the 8th over the u minus 2, like this, I do u to the 8 times u, and u to the 8 times this minus 2. So that means here, u to the 8 times u, let me bring the integral sign over. U to the 8 times u will be u to the 9th minus u to the 8 times 2 will be 2u to the 8th. And all of this will be du. And of course, I have the integral of the difference. I can write this as the difference of the individual integrals. So this means I'll have the integral of u to the 9 du minus, I'll pull the 2 out in front, and that'll be multiplied by the integral of u to the 8th du. And for each integral, I'll increase the power by 1 and divide by the new exponent. So I'm using the power rule. So this u, add 1 to the 9, you'll get 10. Divide that by 10, minus 2 times. For the integral of u to the 8 du, we increase the power by 1, so it'll be u to the 9, divided by 9. And it's an indefinite integral, we must include the plus c. Okay? Now let's do the back substitution. We let u equal to p plus 2. So this will be p plus 2. That quantity is to the 10th power divided by 10 minus the 2 will be in the numerator. And now u was p plus 2. So p plus 2, that quantity is to the 9th power. That'll be divided by 9. And then plus c. So that will be the integral of p times the quantity p plus 2 raised to the 8th dp would be p plus 2 quantity raised to the 10th divided by 10 minus 2 times the quantity p plus 2 raised to the 9th divided by 9. All right, on the next page is the general integration formulas here. Be familiar with these 11 integration formulas here. The first 6 are your trig functions for the integration. Be familiar with those. And they should be familiar because we talked about that in section 4.9. And this time they're having some constant a in front of as the coefficient of x. These next one, 7 and 8, deals with the exponential and the logarithmic functions. And then the last 3 deals with your inverse trigonometric functions here. One for the inverse tangent, one for the inverse sine, and one for the inverse secant. Make sure that you are familiar with those because we will be referring to those general integration formulas in these examples. Like in example 7, let's start off with that. Here we want to use a change of variables or the table that I just showed you to evaluate the following indefinite integral. Here we got the integral of x to the 5th times e to the x raised to the 6th dx. Well, let's work with the e, okay? Because that e has an exponent x to the 6th. Excuse me. So let's use that x to the 6th as our u. So I'm going to let u equal x to the 6th. And then we can take du. Du will have to be equal to 6x raised to the 5th dx. Okay. Now I'm going to rewrite this as the integral of e raised to the e to the x to the 6th times x to the 5th dx. because I do have x to the fifth here. I can get that by itself. It's being multiplied by 6. I need to divide both sides by 6. So here I'm going to have 1 over 6 du is equal to x to the fifth dx. So now let's do our substitution here. This x to the 6 right here, that's going to be what u is. The x to the fifth dx, that's going to be 1/6 du. So here's what I'm going to have. The integral of e to the u times x to the fifth dx, that's 1/6 du. And then I can pull the 1/6 out in front of the integral sign, so it'll be 1/6 times the integral of e to the u du. And the integral of e to the u du, the simplest integral you can take, would be e to the u. So I have 1/6 e to the u plus c. Now let's do the back substitution. We let u be x to the 6. So we need to put that back in, back substitute. 1/6 e to the x to the 6 plus c. And that would be the integral of x to the fifth times e to the x to the 6 dx. All right, now let's take a look at this one right here. Here we got the integral of 4x to the fourth divided by the square root of 9 minus 8 to the 8x to the fifth dx. And I don't think we're going to be able to use one of those inverse trigonometric functions. So what we'll have to do here is just integrate by substitution, by letting the u be what's underneath that square root symbol. So I'm going to let u equals to 9 minus x to the fifth. That u is equal to 9 minus x to the fifth. Then that means du would be this. The derivative of 9 is 0. The derivative of negative 8x to the fifth. Bring the 5 down, multiply by negative 8, you'll get negative 40. Copy the x over to the 1 less power, so it'll be negative 40x to the fourth dx. Okay. Now I'm going to do this right here. I'm going to pull this 4 out in front, so it'll be 4 times the integral of, let's say, 1 divided by the square root of 9 minus 8x to the fifth times x to the fourth dx. And I do have x to the fourth dx here. And I want it by itself, so that way I can do the substitution here. I'm multiplying it by negative 40, so let's divide both sides by negative 40. So here I'm going to have negative 1 over 40 times du, and that's equal to x to the fourth dx. Okay, so now we can do our substitution here. Then 9 minus 8x to the fifth, that would be u. Dx to the fourth dx would be negative 1 over 40 du. Okay, so here's what I'm going to have. The fourth will be on the outside times the integral of 1 over the square root of u times negative 1/40th du. And I'm going to pull that negative 1 over 40 out of the out in front. So I get 4 times negative 1/40th times the integral of that u, square root of u, in its exponential form will be 1 over u to the 1/2 du. And I'm also going to multiply 4 times 1 over 40. Well, when I do that, This 4 goes into itself 1 times, 4 goes into 40 10 times. So that's going to be a negative 1/10. Negative 1/10 times the integral of, and I'm going to pull that u to the 1/2 out of the denominator and write it as u to the negative 1/2 du. So now we got negative 1/10 times, if I increase the power by 1, that would be negative 1/2 plus 1, which would be u to the positive 1/2. Divide that by the new exponent of 1/2, and then plus c. Well, the reciprocal of 1/2 would be 2, so I got negative 1/10 times 2, and then I'm going to back substitute by replacing the u with that 9 minus 8x to the 5th plus c. And then negative 1/10 times 2, that can be reduced by dividing 2 into 10, going 5 times. That 5 will be in your denominator. 2 goes into itself 1 time. So this ends up being negative 1/5 times the quantity, 9 minus 8x to the 5th plus c. Okay. All right. Example 9. Example 9 looks like this. Let's say we got the integral of the square root of x minus 9, and that quantity is to the 3rd power divided by 2 square root of x dx. In this case, I'll just take what's in that numerator and what's inside the parentheses and use that as u. So I'm going to let u equal to the square root of x minus 9. And then du. And if you recall, the derivative of the square root of x is always going to be 1 over 2 square root of x dx. All right. Now, what I'm going to do is rewrite this as the integral of, let's see, square root of x minus 9, and that's going to be cubed, and that's going to be multiplied by 1 over 2 square root of x dx. I'm just breaking this apart so that way you can see what du is going to be, 1 over 2 square root of x, which is exactly what I have right here. That's exactly what I have. So now let's go ahead and do our substitution here. Square root of x minus 9, that's your u. And 1 over 2 square root of x dx, that's going to be du. So here's what I'm going to have as the integral of u raised to the 3rd times du. So now I can apply that power rule to integrate u cubed du by increasing the power by 1. So it'll be u raised to the 4th, divide that by the new exponent of 4. And then, of course, it's an indefinite integral, so we use the plus c. Now we can do the back substitution here. And I'm going to write this as 1/4 times that u, we let u equal to the square root of x minus 9. And that's going to be raised to the 4th plus c. Right, now example 10. Here we got the integral of 1 divided by 5x plus 1 dx. Integral of u of 1 divided by 5x plus minus 1, dx. So in this case, I have to let u equal to what's in the denominator. That's the only way I'm going to be able to use the u substitution. So I'm going to let u equal that 5x minus 1. And then du, we take the derivative of 5x, that's just going to be 5. And then the derivative of minus 1 will be 0. So du will be 5 dx. Well, I got a 1 dx, but here I just want a dx here. So I need to go ahead and divide both sides by 5 so I can do the correct substitution. So that means I have 1/5 times du is equal to dx. Okay, so now let's make our substitution here. We have the integral of 1 over 5x minus 1, we let that be u, so it'll be 1 over u times dx will be replaced with 1/5 du. And the 1/5 can go on the outside of that integral symbol, so it'll be 1/5 times the integral of 1 over u du. And the integral of 1 over u du, if you recall, has to be the natural logarithm of the absolute value of u, and then plus c. So I have 1/5 ln of, now my u, I'm going to do the back substitution, is absolute value of 5x minus 1, and then plus c. And we have to have that absolute value there, because 5x minus 1 could be either positive or negative. So we need to include that absolute value in order for the natural log to be in the domain. Okay, so that's the integral of 1 over 5x minus 1 dx. 1/5 ln of the absolute value of 5x minus 1 plus c. Okay. Example 11 is this. Let's say I want to use a change of variables to find the definite integral, the indefinite integral. And I'll leave the check up to you on this one. So here we got the integral of 1 divided by the square root of 9 minus 64x squared dx. Okay, by looking at this, I see that 9 is a perfect square and 64 is a perfect square. So here, I'm going to write this as this. The integral of 1 divided by the square root of that 9, I can write that as 3 squared, since 3 squared is 9. The 64, well, 8 times 8 is 64, so I can write that as 8x, and then that's going to be squared. Because 8 squared is 64, x and u squared will be x squared. Okay, so pretty much I'm going to be using one of those inverse trig functions, either the inverse sine or the inverse secant. And it looks like I'm going to be using the inverse sine. Okay, and here's what I'm going to have to do here if I'm going to use the u substitution. I'm going to let u equal to the one that has a variable in it and is squared. That's the 8x. And then du will be just 8 dx. And I do need to put that dx here as well. Notice I got 1 dx or just dx here. I need to get dx by itself by dividing both sides by 8. So I have 1/8 du is equal to dx. Now I can do my substitution here in this case. So here I'm going to have the integral of 1 over the square root of that 3 squared, I'll just leave that as is, minus, I'm letting u be 8x, so it'll be u squared, times dx will be replaced with 1/8 du. And the 1/8 can go on the outside of the integral sign, so it'll be 1/8 times the integral of 1 divided by the square root of 3 and it's squared, minus, now put the u here, and that's going to be squared du. And I might as well do the same thing up here to show that the u will be in the parentheses, and it's going to be squared. Okay. Now let's bring down the 1 over 8. This follows, or this matches this right here, the integral of dx divided by the square root of a squared minus x squared, and a is a constant, so it's going to be the inverse sine of my x divided by whatever a is plus c. So in this case, I'm going to have the inverse sine, 1/8 times the inverse sine of this u, that's your numerator. This will be 3. Okay, because since a squared is 9, that means a has to be 3. You have to think of what number squared will give you 9, and this be 3. And then that's just going to be plus c. And now to do the back substitution, you're going to have 1/8 times the inverse sine of u, which was 8x, divided by 3, plus c. Now you can leave it like this, and I think they might have it written like this. Inverse sine of 8x divided by 3. That's in parentheses. Oh, that's over 8 plus c. Okay. All right, now take a look at this next one right here. Let's say we got the integral of the secant of 34w, tangent 34w, dw. Okay. So now we got one of our 6 trigonometric functions that we're going to have to, trigonometric integrals that we need to use here and be familiar with. So I'm going to let u equal to the angle for the secant and the tangent. That's the 34w. And then du, we take this derivative of 34w, which would just be 34, and we write it as a differential, dw. All right, so we need to get dw by itself. We're multiplying it by 34, so we need to divide both sides by 34. So that means dw will be equal to, let's say, 1 over 34 du. Well, all we got to do is just do the substitution in terms of u. So this will be the integral of the secant of 34w is going to be u, tangent of 34w, that's also going to be u, times dw, we replace that with 1 over 34 du. And I can pull the 1 over 34 on the outside, so it'll be 1/34 times the integral of the secant of u, tangent of u, du. Now the integral of the secant of u, tangent of u, we'll go back to that table. The integral of the secant of the angle times the tangent of the angle, that's going to be actually the secant of that angle. So in this case, this will be the secant of u du. I mean plus c. Secant of u plus c. Now doing the back substitution, that u was 34w. So it'd be 1 over 34 times the secant of, 34w plus c. And that's all there is to it for that example there. Okay. All right. On the next video that I will create, we will be going into definite integrals here. So we'll look at a few examples that deal with definite integrals.